Witness the pride of France, the train à grande vitesse, or TGV. Translated, it means high-speed train. But as with all trains, it's the locomotive that delivers the power. And as it rips across its 1,100-mile network, the TGV shows why it holds the title of the fastest locomotive on rails today.
If you can figure out, we are running now at 300 kilometers per hour, and it seems like a dream. It's very easy.
186 miles per hour is the average speed across much of the TGV network. The high-tension wires racing by deliver the TGV's power. From them, 25,000 volts of electricity is transformed into mechanical energy, which is then sent to motors on the train's wheels. Even at speeds like this, inside the TGV, the ride is smooth and steady. But if the engineer spots something on the track outside, there's little he can do to avoid hitting it.
If you see something, then you will just knock it down. Running at 300 kilometers, you would need 3 kilometers to stop. So if you can see something, obviously it's too late.
In 1990, the TGV set the world speed record when it raced to an astounding 320 miles per hour. But by 2007, train officials wanted more speed. So after some modifications, a TGV locomotive was unleashed for another record attempt. To beat the existing 320 mile per hour record, the TGV would have to exceed 516 kilometers per hour.
400.
Après contrôle et validation, la valeur officielle de la vitesse atteinte dans notre marche est de 574,8 km/h. Je répète, 574,8 km/h.
574 kilometers per hour equals 357 miles per hour and a new world record. The remarkable run proved once again that when it comes to speed, the TGV is king of the rails. The TGV might be the fastest locomotive on rails today, but this is what high-speed locomotives used to look like. During the early 20th century, locomotives rarely hit 100 miles per hour. But when it comes to looks, many locomotive fans agree that none have been more smoking than those powered by steam. Like this beauty, built in 1924, the Baldwin Company's number 90. Still running on the Strasburg Railroad in Strasburg, Pennsylvania. Today, it's a tourist train, so it's still possible to climb on board for a ride back to when locomotives like this helped pull America full steam ahead into the 20th century.
Now we're ready to depart. Now I'm going to release the brakes and apply steam to the cylinders through the throttle. Now it's my job not to spin the wheels, so I want to just gradually apply power.
Applying power requires teamwork between the engineer and the man to his left shoveling coal from the tender into the boiler, the fireman.
Now the fireman has to get his fire nice and hot. By experience, he knows when to shovel. It's a coordinated effort. When I need the steam, he has to already have planned on producing.
In the past, you'd burn about 1.5 tons of coal per hour, and a fireman would be on duty for 12 hours. He could burn upwards of 12 to 15 tons of coal a day, just shoveling by hand from the tender.
Igniting coal in the boiler is the first step in producing power. Since our camera would be roasted by the 2,500-degree temperature in there, the best way to see how a steam engine works is by squeezing into a typical locomotive boiler. This one is currently under repair inside the Strasburg Railroad mechanical shop.
Fireman throws the coal through the hole in the rear, lands in this box. This box is called the firebox. Surrounding the firebox is water. The water is all the way around here and is normally carried up to here. It always has to be above the top of the firebox. If it's not above the top of the firebox will melt. So the heat from the fire can heat the firebox steel, boil the water, create the steam that goes up into the steam space, goes up into the steam dome.
Within the steam dome is a throttle. When the engineer engages the throttle lever, steam is released into a pipe, where it travels to the locomotive cylinders. Inside the cylinders, the steam pushes pistons back and forth. The pistons drive piston rods that in turn drive the locomotive's wheels. Regulating the steam pressure inside the boiler is critical. Too little, and the train loses momentum. Too much, and the boiler could explode. The steam boiler's design was inventive, but because coal is fed from the rear, it creates a problem for the engineer.
I can't see very well past this huge boiler. I have to lean out so I can see the biggest perspective ahead of the engine. I am constantly looking for anything that might obstruct us, including trees, including cattle, or anything else that might be problematic.
That's why locomotive designers invented the cow catcher. Okay, it doesn't exactly catch cows. It kind of muscles them aside. But the cow catcher can't shove aside the effects of the inevitable wear and tear that comes with a 100-ton locomotive thrashing around on 2-inch wide rails. Tires especially take a beating. Like a car, a locomotive tire is attached to a wheel. Except these tires are made of steel, and changing one takes some heat.
The tire of a steam locomotive is shrunk onto the wheel. So in order to remove it, we put the fire ring on, we heat the tire up probably to 400 or 500 degrees. As it gets hotter, it will expand, and eventually there'll be a gap between the tire and the wheel, and that tire will be able to swing and slip right off the wheel center.
Add a fresh steel tire to the wheel, and it'll be ready to roll. Easy enough inside the mechanical shop. But in the old days, when things broke down out on the plains, the engineer did double duty as the mechanic.
The technology was constantly breaking down. The engineer had to be aware of any problem arising by both sound and vision.
And when that vision spotted something on the track, it was time to sound off. Every time the toot of a steam locomotive's whistle fills the air, it speaks in a unique yet universal language.
Now, every engineer does his whistling a little bit differently. You'll now hear a crossing signal, 2 longs, a short, and a long as we approach this crossing.
By the 1930s, the sounds of the steam locomotive began to fade as designers looked to new technologies. In 1934, Electromotive launched a line of diesel-electric streamliner locomotives that were easier to maintain and cheaper to fuel than the coal-fed steamers. Today, diesel-electric locomotives have a different look, but they are still the industry standard. Companies like Electromotive Diesel in London, Ontario, build hundreds of them every year for the international market. And every one starts from the bottom up with a single steel bed plate.
What we see here is a domestic bed plate. It's approximately 1 3/4 inches thick, 70 feet long, and 6 feet wide, and it weighs approximately 30,000 pounds.
The bed plate begins its journey upside down, so welders and grinders can add sills and cross members to the underside. the locomotive's underframe is taking shape. Then it's up, up, and away to do the locomotion.
The underframe itself is almost 80,000 pounds at this point.
The upside-down underframe eventually lands in the assembly area. Here, some of the major components are lowered into place.
So what we see here is the compressed air tanks that supply the compressed air for the locomotive as well as the rail cars. And above us, what we see is the loading of a 5,000-gallon fuel tank, which is our domestic fuel tank.
Tighten a few bolts, and the underside of the locomotive is just about locked down. Meanwhile, workers are assembling other parts throughout the plant, like this upside-down wheel assembly. A combination of wheels, gear, axle, and electric motor. This is where the electric part of the diesel-electric locomotive comes in.
We got a 1,000-pound wheel at a 43-inch diameter. We got an 83-tooth gear that weighs approximately 500 pounds with a 9¼ inch diameter axle sitting on an electric traction motor.
Put 3 wheel assemblies together, and you've got a bogie. And this bogie is about to take its first spin. Up and over, until it's right side up. Then it's off to final assembly, where the underframe is taking a twirl of its own. Set the underframe on top of a set of bogies, lower the cab into place, and all this loco needs is some motive. Yep, this is the diesel part.
What we see here is a diesel engine that we use on one of our locomotives. Compared to a normal car engine, a car engine runs around 4 to 6 cylinders, roughly about this size, compared to the cylinders that we use here, and we use 16 of them. When we talk about this engine, it weighs approximately 40,000 pounds compared to a local car engine, which is much less than that, obviously. Also, a local car engine would take around 200 horsepower, whereas this guy right here, our workhorse, runs around 4,300 horsepower. From here, we use the overhead cranes to remove the engine off the stand and deck it onto one of our units.
On board, mechanics hook up the engine to an 8-ton alternator. And the diesel-electric locomotive is ready to rumble. And when it does, here's how it will work. The diesel engine sends mechanical power to the alternator. The alternator transforms that power into electricity. The electricity is then sent to the electric traction motors on each wheel assembly. The motors turn the wheels, which apply power to the track. In the locomotive business, power on the track is measured in tractive effort. The more traction that can be applied between wheel and rail, the more pulling power on the locomotive. Central to tractive effort is managing friction. And the secret lies in the simplest of substances.
What we want here is we want to have good friction on the surface of the wheel where it contacts the actual rail. So how we increase the frictional force between these two surfaces is we use this nozzle and we actually pour sand into this area. What that does is it increases the frictional force, thus allowing more tractive effort to be placed on the rail.
While the sand increases friction to the bottom of the wheel, just inches away, the wheel flange gets a rub with a clever little device that decreases friction.
Here's the frictional force that we don't want. That's between this surface of the wheel and the inner surface of the rail. So what we've done to counteract that is we have this flange lube dispenser that has a graphite-based lubricant that makes contact with this surface. What it does is it applies it as the wheel turns and thus reduces the frictional force between this surface of the wheel and the rail itself.
After all the steel is secured, the bogies are bolted, and the engine and motors are mounted. They make up one of the largest freight locomotives in the world.
Here we are next to a completed domestic locomotive. The locomotive is 75 feet long, 16 feet high, and 10 feet wide. The locomotive itself weighs 425,000 pounds. It's really the workhorse out there in the industry.
But before each of its workhorses is turned loose, it gets ridden hard out on the test track.
So there's full throttle 8. You see the tractive effort build up. And I should get around 4,500 horsepower. This is good. This is a good engine. It'll pull like crazy.
Crazy? How's this for crazy? Nothing like a header to find a locomotive's weak spot. This is TTCI's Transportation Technology Center outside Pueblo, Colorado, the place where the Federal Railroad Administration conducts research, and locomotive manufacturers send their technicians to test their latest designs, to watch train wrecks, and to study the effects for safety and future development.
One of the things that we do here at TTCI is to conduct crash tests. That's one of the abilities that we have at an isolated site like that, and we've done that right on the tracks right behind me here.
In the real world, locomotive crashes like this are rare. And whether the other vehicle is a car or truck that tried to run a crossing, or a train that was mistakenly switched to the wrong track, the outcome is always the same. The locomotive wins. As this crash test shows, the damage caused by the locomotive climbing up and over the train car is extensive and possibly life-threatening to the engineers sitting in the cab. By studying crash test video, manufacturers like Electromotive Diesel, or EMD, are able to develop ways to reduce the risks. Even during the mother of all crashes, a head-on between two locomotives.
For head-on collisions, we've developed an anti-climber. This whole structure is the anti-climber. It is designed to resist a strong upward force here and keep the coupler from coming up over the main structure here and the other car going into the cab.
When two locomotives without the anti-climber collide head-on, the locomotive with more momentum can slide straight up and into the other's cab. But if one locomotive has an anti-climber, the coupler from the other locomotive catches underneath the anti-climber, stopping upward motion and diverting the energy laterally. The EMD anti-climber, first used in 1989, is now the industry standard.
The crashworthiness of the locomotives used in North America is the best it's ever been, largely as a result of the kinds of tests that we do here, the activities of people like EMD in applying that information into the design of their cabs.
Out on the TTCI test track, EMD engineers are evaluating their newest design element, what they call the isolated cab. Their goal is to have the quietest cab in the business.
We're trying to control the working environment. The whole purpose is to keep the noise down inside the cab from the 4,500 horsepower that's just 20 feet behind us.
EMD has tried to reduce the noise and vibration inside the cab by separating it from the engine compartment. To record the decibel level, technicians have hung microphones at ear level throughout the cab. The target is 80 decibels or less. Then it's time to open up the throttle to see if the isolated mounts work. Even at full throttle, the sound level barely exceeds 75 decibels, about the same as a normal conversation between two people, and a victory for the EMD designers. And while they're here, the crew is also collecting ride quality data by testing the cab for vibration.
The whole cab has a number of sensors all over the cab, one of which is right here, where we measure the cab's seat base vibration in all three directions, up and down, fore and aft, side to side.
Technicians record the data in a test car behind the locomotive. Later, EMD will use the data to develop even more ways to improve its locomotives and keep its operating engineers safe. In another area of the test facility, TTCI offers locomotive makers a way to look through steel with its automated cracked wheel detection system. The system uses sound waves to take a snapshot of a locomotive's wheels as they pass through an ultrasonic sensor.
Right now, this first wheel is going to be picked up by this inspection site. It's going to follow it all the way through. Once it follows it through, it's going to reset itself, set up for the next wheel that comes through. It'll pick it up, it'll send ultrasonic energy up through the wheel and inspect the wheel for cracks. And then that information will be transmitted into our computer bungalow.
Inside the bungalow, the results appear on a computer screen in real time. Each rectangular box represents a wheel. The lines reveal some type of flaw.
Right here, you're showing some thermal cracks in the locomotive wheel. Here, you're showing a horizontal crack. So then it triggers the maintenance crew on what they need to do in order to correct that.
Whereas TTCI exists to help find a locomotive's flaws, a network of service stations across the United States stands ready to fix them. One of the best is the CSX Maintenance Facility in Waycross, Georgia. CSX Transportation runs the largest railroad operation in the eastern United States. Every day, thousands of CSX locomotives traverse the country, hauling freight. Keeping them operational is crucial to the bottom line.
Time is money, and these locomotives cost about $2 million a piece, and if they're setting, we're not utilizing that asset. We can service as many as 12 at one time. This is simply a service station for locomotives.
And this service station is built for speed. It's kind of like a NASCAR pit stop for locomotives. The moment a locomotive pulls in, a team of workers moves into place. The aim is to get it in and out in under an hour.
And this is where it starts here at the Locomotive Services Center. We'll service anywhere from 75 to 100 locomotives at this facility per day. Here's where the sand will be going in. It'll be coming in through a funnel that he'll put in. Here we have a gentleman that's going to be changing a flange lube stick to help with the flange wear when we're going into curves on the track. Here the gentleman's checking the oil and the water. He's going to make sure everything is in good running repair with the diesel engine. Here we are adding fuel to the locomotive. The locomotive fuel tank will hold anywhere from about 1,500 gallons up to 4,500 gallons. At this facility, we will pump about 100,000 gallons of diesel fuel a day.
His workers handle the basics from above. Others are busy in the service pit below.
As they're working up above, they're also going to be changing brake shoes down below. Warren is going to be pulling this brake shoe out and going to be replacing it with the new brake shoe. He has to remove the brake key, take the old brake shoe out, replace it with the new brake shoe, and then drop the brake key back in that holds the brake shoe in place. And it's ready to go. Here we have a worn brake shoe that is in need of being replaced. Here we have a new brake shoe that we will put in its place. The new brake shoe should last approximately 3 to 4 weeks, depending on the amount of traffic the locomotive is involved in.
Of course, there are times when some heavy lifting is required. For those cases, locomotives make a trip to the back shop, where mechanics carry out everything from cosmetic repair to complete engine rebuilds.
We do lots of accident damage. That could be crossing accidents that happen out on the line of road. We change main alternators, and we just do lots and lots of work, more or less rebuild the locomotive in that area.
Once most locomotives are cleared to return to action, they get a final sprucing up with a quick shower in the CSX wash.
It gets a lot of the road film off of them, because after all, CSX, that's what's on the side of the locomotives. We're proud of our company, and we certainly want to look good in the public's eye.
But sometimes looks can be deceiving. Ever see a 70 million ton ship steadied by one little engine that could? Unlike the little engine that thought it could, these mini locomotives along the Panama Canal know they can. Nearly 14,000 times a year, they slowly and steadily guide ships through the 3 locks that connect the Pacific and Atlantic Oceans. Here, size matters less than precision. The locomotives measure just 13 feet high, 10 feet wide, and 35 feet long. But there's nothing small about the economic stakes of their mission.
The fee that we charge to the ships depends on the size of the ship. There's a cruise ship on the right side. Those are the ones that pay the most on tolls, approximately $200,000 each.
At these prices, the 40 shipping companies that send vessels through the canal every day expect to do it safely and efficiently. Like the 70,000-ton Panamanian cargo ship coming in from the Pacific.
The chamber is very small for this ship, and it's a slow operation, and the locomotives are very critical for handling a ship of this size.
As the ship approaches the lock's mouth, 8 locomotives, 4 on the starboard side, 4 to the port, move into position. The ship is 106 feet wide. The lock chamber is just 110. And for the next half mile, the little locos will be guiding the ship to the end of the lock. The carefully choreographed journey begins as canal ship personnel throw a line to be fastened to 2 steel cables that are attached to the winches on the side of the locomotives.
The idea is to get the cables of the locomotives onto the ships. As you can see, there are 2 locomotives taking care of the bow of the ship. Then we're going to see 2 more taking care of the back of the ship, the stern.
All 8 locomotives are under the direction of a specially trained pilot aboard the ship, who works for the canal. His first command to the locomotive operators is to pull their cables tight until the ship is securely tethered in the center of the lock. Then it's locomotives and ships ahoy, as the pilot gradually powers his ship forward, while directing the locomotives to move in unison with him. From here on, it's all about keeping the sides of the ship's steel hull off the cement walls that line the lock.
As you can see, the ship is very close to the wall. The same thing is happening on the other side. So they should be able to coordinate with the pilot to keep the ship as much in the center as they can. There's only 2 feet on each side. Any little mistake, you can rub the ship against the wall and cause a damage.
Top speed for the locomotives is 10 miles per hour. But with a ship this size, and so little room for error, they crawl along at about 3 miles per hour. Even at this speed, mistakes are costly. So to minimize any confusion between ship captain and locomotive operator, there are no conversations, just orders and action.
The operator listens to the orders from the pilot via radio, and every time he hears a command, he has to ring the bell to acknowledge that he received the order. He operated a locomotive basically 2 main functions. Traction with this hand is moving the traction control, and on the left, he has the controls for the cables, or 2 cables. 1 control for each cable. He's holding the ship in the center together with his partner on the other side. Asking number 1 center to coil. They don't have to do anything here, just keep the cables tight. He's moving ahead now a little bit.
While the ship remains under its own power, the locomotives are propelled with electricity via a shoe that's connected to the rails. The rails are energized with 480 volts. In the middle of the track, a steel gear pulls the locomotive along. The electricity comes from below, inside a specially designed power station that runs the length of the track.
We are inside of the machinery tunnel, right underneath of the locomotive tracks that runs all along the lock walls. And here is where the locomotives get their power from. This is a transformer that brings the voltage down from 2,400 volts down to 480, the power required by the locomotive. These are the main breakers for the power that is fed to the locomotive above us.
Up above, the Panamanian ship is now inside the lock chamber. As the lock fills with water and the ship rises, it's steady as she goes for the locomotive operators.
During this time, the locomotives just have to keep the ship in the position with the cables tight. That way we'll avoid hitting the walls and we keep the ship safe.
Keeping a 140 million pound ship centered in the lock requires some tension. Most of it is focused in the cables. So the cables are routinely tested to withstand twice the amount of stress they'll ever need out on the lock. For the locomotive engineers, stress comes from the one thing they all fear: a dip in the drink.
The cables are very tight, so the locomotives are pulling very strong. To avoid the locomotive overturning into the water, we have the safety wheels. That's what we use, the safety wheels. They are attached to this piece of track, so the locomotive is always secure to the track. No matter how much force they put on the cables, they will always stay on the track.
Of the thousands of passages during the canal's nearly 100-year history, just 1 locomotive has been pulled sideways into the canal. And that was due to human error. A closer look reveals the virtually accident-proof safeguarding system.
Here we are underneath the locomotive in the maintenance pit. Here we can find the safety wheels. These are the ones that prevent the locomotive from tilting and going into the water.
The gates of the lock are open. Like countless ships before it, the cargo carrier is about to leave its tight squeeze here for the open waters of the Pacific Ocean.
The ship is ready to get out of the locks. We're reaching the end of the sidewall. He just asked number 3s to release the wires and cast off. So he's going to cast off the number 3s, the guys in front of us. He just asked foresight us to cast off. So he's going to release the wires and cast off. He's giving the signals so the deckhands can release the cable from the bit on the ship. They're going to let go anytime. And here they come. Okay, so we're off the ship.
45 minutes after it entered the locks, another vessel has completed safe passage. For the little canal locomotives, a long line of customers is waiting at the lock's entrance. If you want to ride one of these locomotives, you'll need to take an elevator to get to it, some 600 feet underground. 600 feet underground, inside the Bailey Mine in southwestern Pennsylvania. A fleet of some of the most unusual locomotives is busy ferrying miners and equipment through a labyrinth of tunnels that spans hundreds of miles. Miners have been pulling coal out of the mine since 1984, and some of the original locomotives are still in operation. The fleet is powered by 3 different sources: external electrical, battery, and diesel. The electric locomotives are attached to an overhead trolley line and to its obvious limitations.
This is a very old battery trolley unit. It's powered, it gets all its power from the overhead trolley line. That technology's been used in the mines for decades. The problem with the older technology is he has to be underneath this to operate. When he goes away from a trolley line, he's dead.
Another drawback to the outdated trolley line is the 300 volts hanging from above, just waiting to take a bite out of anyone who accidentally touches it. Power outages create yet another problem.
If you have any power problems or anything drops out, then that piece of equipment has no use. I mean, any power problem in the mine, or if you had to get out, you would have none.
The mine's battery-powered locomotives eliminate the need for an overhead trolley line. But locomotive batteries don't keep going and going.
You have to actually take it into a charging station and charge it. You're losing the use of your piece of equipment while you're actually charging it.
Everything considered, the power source that most miners prefer may surprise you: diesel.
Diesel is much safer. You no longer have the hazards of any short circuits in your coal mine and the potential for mine fires. With diesel, you're totally in control. I expect to have Bailey Mine converted entirely 100% to diesel, because I do believe diesel is the future for track-mounted equipment in the coal mine.
Wondering how Bailey's miners coexist deep underground with a herd of diesel-burning locomotives spewing out exhaust? Brookville Equipment Corporation in Brookville, Pennsylvania, has been building underground diesel locomotives since 1980. And they have the answer to the diesel question.
A lot needs to go into the safety and the health of the people working in that environment. This is a 170 horsepower diesel engine. It's MSHA approved for underground use. The engine manufacturer has to take it through a series of tests where they measure the particulates and they give it a certification.
Brookville has also installed a state-of-the-art filtering system, sure to keep miners breathing easy.
To run the diesel engines underground in a coal mine, you have to have an additional exhaust treatment system. The exhaust comes out, goes through a catalyst, which breaks apart the diesel particulate matter. The exhaust gas comes up into this filter housing, where a replaceable paper filter element is used to capture approximately 95% of the diesel soot that is emitted from the engine. And that's why we don't smell diesel engine in here, diesel fuel. You put it in the box that the new one comes in, and it's acceptable in any landfill.
For a typical Brookville diesel locomotive, nearly 2,000 parts are cut, drilled, forged, and assembled, while the diminutive frames get built separately.
Engine sits in the front here, transmission in the center. You can see the 2 wheel wells, and these are grids.
for airflow, and the operator compartment up front. These are 23-ton locomotives.
Down in the Bailey mine, a Brookville diesel-powered personal carrier is filling up for the morning commute.
You can see the men in here, they're getting ready for their shift to begin. You can see the operator station of this vehicle. He has all the controls that tell him the full function of the engine, the brake and throttle. These guys got to go to work. They can go 10 to 12 miles an hour on good track. It's a whole lot faster than walking.
Every day, 80 different underground vehicles travel throughout the mine. And every day, at least one of them derails. Brookville's got that covered, too. Now operators can get things back on track with the rail walker.
The old way is using a hand jack or a railroad jack. Very labor-intensive and relatively dangerous. The new way is hydraulically. So what we did, we hydraulically lifted the locomotive by putting a foot down on the ground, raising the locomotive, and moving it sideways. Position it back over the rail. It's moving back into position, the wheels being lowered gently in a controlled manner back down on the rail.
With innovations like the rail walker and the clean-burning diesel engine, miners can move around safely and efficiently, some 600 feet underground. Up above, there's a new locomotive that's designed to stay off the rails. And one American company is trying to catch up and pass the international competition. Here's a game changer, the new world's fastest locomotive. It's called the maglev, a high-speed train system being used commercially in China and Japan. During a 2004 test run in Japan, the maglev rocketed to 361 miles per hour, the fastest speed ever recorded for a train. We know we said the French TGV was the fastest, but which one deserves the title depends on your definition of a locomotive. You see, an engine doesn't power the maglev. It's powered by the track. Paradoxically, the maglev train never even comes in contact with the rails.
It's basically riding on a cushion of air. It's propelled by invisible magnetic forces. The locomotive, if you will, is magnetically levitated, propelled, and guided.
On General Atomics test track in San Diego, California, engineers are working on a maglev system for America. If everything goes right, maglevs can be running in American cities within a decade. This prototype system is designed around the same basic law of physics as the maglev systems in China and Japan. Take some magnets, make a special track, apply power, and it's up, up, and away. The maglev track, or guideway, is lined with a cluster of electric power cables called a linear synchronous motor, or LSM. The train carriage is joined to a set of magnets that wrap around the track. When the linear synchronous motor is energized, it generates a moving magnetic field, creating a magnetic wave that pulls the train carriage forward. To increase speed, more power is added to the LSM. As the carriage moves forward, the electricity shuts down behind it. That leaves the issue of levitation.
Let me tell you about how the levitation system works. We get levitation by virtue of currents that are induced in this track. The magnets are in this wraparound structure. They're inside these cans, and we use a set of magnets for levitation.
For the levitation to occur, the magnets are aligned in a formation called the Hallback array.
The way the levitation system here is going to work is that these arrows indicate the polarity of the magnets. That basic configuration is nothing more than each of these magnets is rotated by 45 degrees. What it winds up doing is it produces a sine wave that is focused on the track. It goes in through here, it returns off here, it hugs the backside and comes out, and it tends to focus the magnetic field on the track where you want it.
In layman's terms, what that means is that the wheels are going to lift off the track. All the magnets need is some forward motion. On the track, the electric cable's provided. In here, the spinning wheel induces the power.
And actually, what you're seeing right now is that basic principle of levitation. We're levitated to well over an inch, and the levitation force is maintained as long as there's forward motion. When we're coming into a station and we're slowing down, then we're going to gradually get less and less of an air gap until we're almost at the station here. As we come in, we're just about now landing on the wheels and we come to a stop.
Build up enough speed and it's time for the landing wheels to lift off.
When the speed of the vehicle reaches approximately 10 miles per hour, enough current is induced in the track that it produces levitation of the entire structure, including the magnets as well as the wheels here.
By levitating the carriage above the track, you've got a frictionless system. That's the key to generating speeds up to 350 miles per hour. Like the maglevs in China and Japan, the proposed system would require its own dedicated track. But the separate track is also one of maglev's advantages. No rail crossings. There's also no need for an engineer. The system is completely automated, run from a control room where all operators have to do is program the motor to induce the right amount of power ahead of the carriage. But the General Atomics proposed system has one major difference from the high-speed Asian versions.
We're focusing our technology on lower speed operation, urban systems, up to about 100 miles per hour. We feel that there's a real market for alleviating much of the congestion that we find in many of our cities.
By late 2009, General Atomics hopes to begin construction of a maglev demonstration system on the campus of the California University of Pennsylvania. Building the maglev system will cost up to $40 million per mile.